Hello, and welcome to Part 2 of Hitachi Cable America's Introduction to Fiber Optics. This training presentation is directed at educating Hitachi customers by providing information that develops a working knowledge of fiber optic product technology so that people in the sales channel feel comfortable to include a fiber optic product solution along with Hitachi's copper category cable products. This presentation is comprised of 4 parts. The 4 parts are optical fiber components and types, optical fiber standards, fiber cables and applications, and how to field a fiber cable inquiry. Introduction to Fiber Optics Part 2. Optical fiber standards and specifications. This presentation will familiarize you with the optical fiber standards, terminology, and specifications associated with all fiber optic applications. There are 6 types of standard optical fibers, 4 types of multimode fibers, and 2 types of single-mode fibers. Multimode fibers are designated by an OM abbreviation. Single-mode fibers are designated by an OS abbreviation. Each standard fiber spec, OM1 through OM4 and OS1 to OS2, have unique attenuation performance requirements, and multimode, OM1 through OM4, have an additional performance rating called bandwidth. This chart graphically illustrates the optical fiber standards differentiated by the fiber core size. OS1 and OS2 is a 8 to 10 micron core single-mode fiber. OM1 is a 62.5 micron core multimode fiber. OM2 through OM4 is a 50 micron core multimode fiber. As mentioned, each OS and OM standard has a specific performance rating. OS1 and OS2 fibers represent solutions for new generation systems such as 40 gigabits per second and 100 gigabits per second Ethernet found in enterprise data centers or long-distance telecommunication applications that would extend beyond the reach of a multimode fiber by using coherent longer wavelength lasers at 1310 and 1550 nanometers. OS2, which has a lower attenuation and is also bend insensitive, is more preferred. Single-mode OS1 and OS2 have no bandwidth requirements, as single-mode has virtually unlimited bandwidth. The information carrying capacity is only limited by the light source and the attenuation over distance. Note that single-mode fibers are designed to operate at longer wavelengths, 1310 nanometers and 1550 nanometers, than multimode and carry a light signal over long distances. And at these wavelengths, single-mode fiber is very effective and provides very low attenuation properties. Looking at the 4 multimode optical fiber standards and application examples, OM1 and OM2 fibers represent solutions for older generation legacy systems such as FDDI, Fiber Distributed Data Interface, and Fast Ethernet 10x100 that are still operating today and designed for data rates up to 100 megabits per second. These fibers may also be used in industrial process control applications that typically operate at lower data rates and want to take advantage of fiber's immunity to electrical interface. OM3 and OM4 fibers represent solutions for newer generation systems such as 1 gigabit per second, 10 gigabit per second, and 40 gigabit per second Ethernet found in campus networks and enterprise data center applications. Note that there are 2 new product trends developing. OM4 Plus is a trending product that allows for an increased channel length for high data rate applications superior to OM4. Wideband multimode fiber, another new product development trend, which allows for high data rate applications to be multiplexed over a single fiber at an 850 nanometer multimode wavelength. This chart shows the minimum bandwidth and maximum attenuation requirements for each multimode optical fiber standard. Optical fiber performance values are set, measured, and normalized at a kilometer distance, 3,280 feet. Taking a close look at bandwidth, the information carrying capacity of the fiber, the chart shows multimode fibers with 2 bandwidth specification categories, OFL, overfill launch, and min-EMBC, minimum effective modal bandwidth calculated. Today, the primary multimode fiber size being specified is 50 micron. Note, 50 micron, OM3, OM4, and OM4 Plus are laser optimized to provide the highest bandwidth at 850 nanometer in min-EMBC categories. As seen from the previous slide, multimode fiber bandwidth can be characterized 2 different ways, OFL and min-EMBC. OFL, overfilled launch, is defined as a condition where the light source exceeds the acceptance angle of the fiber core, ensuring all possible light mode paths are fully energized, which provides a bandwidth value if the fiber is used with LEDs. Min EMBC is a bandwidth value resulting from analyzing the results of several VCSEL, vertical cavity surface emitting lasers, launching across a fiber core, using the extremes of standard allowable laser sources, to characterize a number of possible laser/fiber combinations and determine, by calculating the minimum bandwidth value when applied to laser-optimized multiple fibers, OM3 and OM4. A LED launch and a VCSEL launch is easier to understand in looking at the next slide. This slide shows the difference between an LED launch that overfills an optical fiber core, energizing all light mode paths, and a VCSEL light source that only energizes several light mode paths when launched into a 50-micron core. With a restricted launch of a VCSEL light source, mode delay may greatly vary depending on fiber imperfections and what area of the core the light is launched into. The next slide demonstrates this effect. This slide demonstrates the range of different light mode paths that can result when several 8-micron VCSELs launch into a 50-micron fiber. A wide range of industry-approved standard VCSELs from different manufacturers introduce a variety of possible performance differences affecting bandwidth and where in the core of the fiber these different VCSELs are launched. EMB calculates a range of different scenarios to come up with a minimum bandwidth of an OM3 or OM4 fiber, which are optimized for 850 nanometer lasers. Why has the industry decided to concentrate on the use of OM3 and OM4 optical fibers? The answer is cost. The bandwidth optimization of OM3 and OM4 at 850 nanometer, as it is seen in specifications, allows equipment manufacturers to utilize low-cost VCSELs in their transmitters. VCSELs provide high data rate transmission at distances greater than copper cables can achieve. A VCSEL, having a narrow spectral width of a laser, exhibits good modal and chromatic dispersion properties that can take advantage of a high bandwidth property of a laser-optimized fiber. Looking at the core size difference, coupling light into a multimode fiber is easier, and the cost of LED and VCSEL light sources are far less expensive than lasers required for use with single-mode fibers. OS2 single-mode fibers are better reserved for the highest data rates of 100 gigabits per second and sometime in the future 400 gigabits per second, and long-distance applications above 1 kilometer. The lasers associated with single-mode applications are very expensive and often require wavelength division multiplexing, the use of several lasers multiplexed into a single fiber, or several serial lasers running parallel over several fibers. In either case, single-mode multiplexing is very expensive, up to 10 times the cost of a multi-mode solution if it is used in short-distance applications. Fiber optic transmission is generally designed around pairs of fibers, one for transmit and receive in one direction, and the other for transmit and receive in the other direction. That's why 6, 12, and 24 fiber counts in cables are very popular in all fiber specs OM1 to OS2. As data rate applications increase, efforts are made to continue to utilize low-cost VCSEL transceivers while still maintaining the maximum distance. The diagram represents the most common serial transmit and receive termed full duplex transmission. At 10 gigabits per second, OM3 and OM4 will carry a signal between 300 and 550 meters. For high-speed data and long-distance applications, parallel and wavelength division multiplexing methods are commonly used. Serial parallel transmission represents a solution used in enterprise data centers. In this example, the 40 gigabit signal is electronically demultiplexed into 4 parallel 10 gigabit signals, still utilizing low-cost VCSELs at 850 nanometers, then electronically multiplexed back into a 40 gigabit signal at the receiving end. Distance is currently limited between 100 and 125 meters. Wavelength division multiplexing represents a solution reserved for longer distances or very high data rates utilizing longer wavelength lasers in the 1,310 nanometer second window or 1,550 nanometer third window. In this diagram, 4 lasers, each with a discrete and different wavelength carry, a unique and dedicated application optically multiplexed into a single fiber. Now that we have reviewed what optical fiber is, how it works, and have looked at current high bandwidth optical fiber standards, we can now answer the question of why is fiber used for high-speed data networks? Optical fiber solutions provide superior data transmission performance in comparison to copper cable solutions for the same applications. Primary benefits are immunity to EMI and RFI interface. Fiber optic signals are immune to electromagnetic fields created by electrical currents generated by power or signals through copper conductors. In comparison, fiber optic transmissions do not require shielding or grounding as do copper solutions passing through areas of high electrical noise. Data carrying capacity and distance. Optical fibers, high bandwidth and low attenuation allow systems to operate over greater distances at high data rates, ideal for large campus networks and building-to-building connections. In contrast to copper solutions, which become more limited as signal frequencies increase. The net result is fiber optic data transmission is ideal for high-speed backbone data applications, reserving copper data cables for the shorter horizontal links to edge devices and workstations. Fiber and copper products work together to provide a total solution. This slide shows several current Ethernet applications and corresponding installation distances of copper category cables and the associated fiber optic cables for the same application. Notice in this chart that category cables lend themselves to high connectivity uses in the horizontal plenum environment, highlighted in orange, and fiber optic cables lend themselves to longer distance backbone applications, highlighted in green, found in building-to-building, outdoor, and vertical riser uses. The next two slides graphically demonstrate distance and bandwidth comparison of Category 6A and an OM3 fiber for 10 gigabits per second Ethernet application. This slide compares the currently popular system reach of Category cable Category 6A to OM3 optical fiber and shows system reach of 100 meters for Category 6A and 300 meters for OM3. OM3 optical fiber offers 3 times the system reach over Category 6A, reinforcing the previous slide that category cables are best suited for horizontal applications and optical fibers are ideal for backbone applications. This slide shows bandwidth comparisons normalized to megahertz per kilometer of Category 6A to OM3 fiber. OM3 has approximately 10 times the bandwidth over the same distance. The same approximate difference is also seen comparing bandwidth of a copper Category 6A cable at 100 meters. The bandwidth difference, again, supports the use of optical fibers for extended system reach for backbone applications. So what are the predictions of continued growth of high data rate Ethernet applications? This slide shows the history and the forecasted growth of the Ethernet switch market for enterprise data centers and campus networks over a 10-year span from 2012 to the year 2022. The transition to higher speed networks will drive the growth and further development of category cables and the expanded use of high data rate optical fibers, both single mode and multi-mode. 1 gigabit per second applications are in blue, 10 gigabit per second applications are in red, 40 gigabit per second applications are in green, 100 gigabit per second applications are in purple. It is expected that older 100 megabits per second systems will begin to be obsoleted and upgraded to 1 gigabit per second and 10 gigabit per second systems over the next several years, most likely using OM3 and OM4 fibers. 40 gigabit per second and 100 gigabit per second applications will begin to focus on use of OS2 fibers. Thank you for participating in Hitachi Cable America's Introduction to Fiber Optics, Part 2.